Number 23. For the following exercises, use the rational zero theorem to find all real zeros. Now before I start, I need to discuss with you one little thing about the rational zeros theorem. It doesn't guarantee that a polynomial with integer coefficients will have rational zeros. It merely states that every rational zero, and at that point you should say to yourself, if any exist, has a certain form. Okay, so for example, this is not problem 23, but here's an example. X to the fourth minus 4x cubed plus 8x squared minus 8x minus 5. That has plus or minus 1 or plus or minus 5 as the possible rational zeros according to the rational zero theorem. Okay, since the leading coefficient here is 1, then the possible rational zeros are the factors of the constant term, negative 5. So you get plus or minus 1, plus or minus 5. But if you try any of those, all of those, none of them give you a 0. Okay? The only zeros for this polynomial are 1 plus or minus square root of 2 and 1 plus or minus 2i. So I'll just box that off so we don't confuse that with number 23. Alright, so there are no rational roots for this polynomial, even though the rational zeros theorem suggests possibilities. Alright, so be advised of that. In all the problems we're doing in this section, the rational zeros theorem will work naturally because they want you to get practice with it, but don't come away from it with the idea that the rational zeros theorem will always guarantee that you're going to have rational zeros, because, okay, it's not true. So it just gives you the possibilities if any rational zeros exist. Okay. All right, anyway, let's go to 23. We've got 2x cubed plus 7x squared minus 10x minus 24 equals 0. So I'm going to write the possibilities for P over the possibilities for Q. In other words, the factors, P represents all the factors of the constant term, and Q represents all the factors of the leading coefficient. All right. So for the constant term, we've got plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, and plus or minus 24. And then the possibilities for the leading coefficient, the factors rather, are plus or minus 1 and plus or minus 2. Alright. Now I'm going to put these together and write a fraction P over Q. So we have possibilities for P over Q. And that's what we're looking for. These are going to be your possible rational zeros. Rational numbers, remember, are fractions. All right. So what you do is you take these possibilities and put them over each of these. So start with plus or minus 1, put it over plus or minus 1. That gives you just plus or minus 1. And then you go to the next one in the denominator, plus or minus 1 over plus or minus 2. That gives you plus or minus a half. And you keep doing this. Plus or minus 2 over plus or minus 1. You could do it this way. Just work with the first one here and do all of these. And then you could go to the second one and do all of these. Or you could alternate here and here like I just did. It doesn't matter. So we've got plus or minus 2 over plus or minus 1 is plus or minus 2. Plus or minus 2 over plus or minus 2 is plus or minus 1. We already have that. Go to the next one. Plus or minus 3 over plus or minus 1 gives you plus or minus 3. Plus or minus 3 over plus or minus 2 gives you plus or minus 3 over 2. Plus or minus 4 over plus or minus 1 gives you plus or minus 4. Plus or minus 4 over plus or minus 2 gives you plus or minus 2, which we already have. Go to the next one. Plus or minus 6 over plus or minus 1 is plus or minus 6. Plus or minus 6 over plus or minus 2 is plus or minus 3, which we have. So over here we got plus or minus 12 over plus or minus 1 is plus or minus 12. And plus or minus 12 over plus or minus 2 is plus or minus 6. And we've got that over there. So on to the next one. Plus or minus 24 over plus or minus 1 is plus or minus 24. And plus or minus 24 over plus or minus 2 is plus or minus 12, which we already have. So that's all we have, all the possibilities for rational roots. So usually we'll try one or try the first one in the list, see if we get a zero remainder. If we find a zero remainder, then we've found our root, or one of the roots. All right. So use synthetic division. 2, 7, negative 10, negative 24. All right. All right, we can see it's not going to give us a zero remainder. Okay, so this doesn't work. How about negative 1? And we've got 2, 7, negative 10, negative 24. And that's not going to give us a zero remainder, so that doesn't work. Okay, well, we could go to a half. Let's, having done this already, let's try 2. But basically what you have to do is go through each of these possibilities using synthetic division and hope you get to the zero remainder as soon as possible. All right, you might end up, if this were like a problem in real life, you might end up going through all of these and not getting anything works, right? So you'd have to try something else. But I think this is going to work. Oops, that should be a something else. Alright, that should be a 12, and 2 times 12 is 24. There's our zero remainder. Alright, so this part right here is a quotient, and if you were doing long division, that would be a quotient. That would represent the coefficients of the quotient. 2x squared plus 11x plus 12. Okay. And this can be factored. X plus 4, 2x plus 3. Alright. So, again, this one works. I'll put a check mark by it. Okay. Alright. So, we want to find the zeros. So we know that this represents x minus 2, which is a factor of this. X minus 2 is a factor of that. And then we've got x minus 2 times x plus 4 times 2x plus 3 is equal to this polynomial. So you want to find the zeros. So we know 2 is a 0. How about the zeros for these? Alright, so set x plus 4 equal to 0. So x equals negative 4. And then set 2x plus 3 equals 0. And then solve that for x. You get x equals negative 3 halves. Alright, so the zeros are 2, negative 4, and negative 3 halves. Number 25. Okay, I've got the polynomial up there already. Now the leading coefficient is 1, so the possible rational zeros will all be factors of the constant term negative 80. Alright, so possibilities for our rational root, or rational roots P over Q. So just the factors of 80, plus or minus 1, plus or minus 2, plus or minus 4, and it's always going to be plus or minus, so if you do this on a scratch paper, there's really no need to write plus or minus all the time. You could put a big plus or minus in front of all of these if you wish. Alright. If this were a test situation, I would write it down like this just to be sure you don't get marked off for something like that. Alright. Plus or minus 5, plus or minus 8, plus or minus 10, plus or minus 16, plus or minus 20, plus or minus 40, plus or minus 80. Alright. So I'm going to try a few here, a couple, and they won't work. And then I'm going to jump to the one that works. Alright. Later, I'm just going to do the one that works. Okay, so in interest of saving time and space on these videos, alright, so when you're actually doing this, I'm afraid you're going to have to go through each and every possibility until you finally strike gold. Alright, so good luck to you in your gold prospecting, and I hope you get it quickly, but you may end up going through everything and then the last one is the right one. So yeah, I've been there and done that. Okay, so you know, that's part of the game here. Well, not really a game, but that's the way it works. So we'll try one. That's what we usually end up trying first. 1's a nice simple number. Okay, we're not going to get a zero remainder here, so go to -1. Remember, there's plus or minus each of these, so you've got to try each of those, plus or minus. That's not going to work. Alright. If you try plus or minus 2, that doesn't work. Try +4. Hint, hint. +4. I've got a feeling about this one. Maybe if one of you knows how to douse for water, right? Use the little rods to find water. If you're good at it, maybe you can do the same thing with this. Get your little rods out and see which ones they point to here. That would be a cool trick. Alright, so let's see, we've got 4, 9, 36, and 20, and +80. There's our zero remainder. That's what we want. Check. Alright. So using what we see here, I can write this polynomial in factored form, at least a partially factored form. X cubed, let's see, plus 5x squared minus 16x minus 80 equals x minus 4 times, that represents, since the original polynomial is x cubed, this is going to be 1 degree less, 1x squared, or just x squared, plus 9x plus 20. Okay. Now, you could keep going with synthetic division. At this point, I would try 4 again, because there may be a multiple root, 4 multiplicity 2 or something like that. But really, you can factor this, and it's just easier to go ahead and factor it. Alright, so we've got x minus 4, and then x plus 4, and then x plus 5. So when you end up with a quadratic polynomial as part of the one of the factors, you could factor it, or you could solve that by completing the square, or use a quadratic formula. All right, it's your choice. Instead of continuing with synthetic division. Now you set all this equal to 0 and solve for x, and you will get the following zeros. From this one you get x equals 4. From that one, -4. And from that one, -5. So you set each of these factors to 0, solve each of those separately, and you get your zeros. There you go. Okay, number 27. So it's written up there. And let me write the possibilities for P. Over possibilities for Q. Alright. So you look at the factors of 15. You've got plus or minus 1. Plus or minus 3, plus or minus 5, and plus or minus 15. And then for 2, the leading coefficient, factors are plus or minus 1, plus or minus 2. Alright. So we can then write the possibilities for P over Q. So you can start with the 1 and then put that over the first one in the denominator. So you got plus or minus 1. And then you can go to the next one here, plus or minus 3, put it over the 1. That's plus or minus 3. Plus or minus 5 over 1 is plus or minus 5. And then 15 over 1, plus or minus 15. Then plus or minus 1 over plus or minus 2. That's plus or minus 1/2. Plus or minus 3 over plus or minus 2 is plus or minus 3/2. And then plus or minus 5 over plus or minus 2, that's plus or minus 5/2. Plus or minus 15 over plus or minus 2 is plus or minus 15/2. Alright. So, again, I usually would start with a 1, but neither of those work. I'm going to just jump right to the one that works. Alright, so again, remember, when you're doing your homework, you should do at least a few of these, going through every possibility. Alright, you could sneak a peek in the answers section and get which one's going to work right away. Alright, if you feel comfortable with your ability to be able to do this, if this were, say, a test situation and you didn't have the answer, right? If you feel comfortable, then I guess I would do the same thing. I'd look at the back and then show my work that way. Alright, but maybe your professor, your instructor might tell you, I want to see all of those possibilities on there, you know, so whether they work or not. Okay, well, you're just going to have to go with the flow. But to save time, like I said, I'm just going to jump right to the one that works. It's a -3 works. And let's see, we've got 2, -3, -32, and -15. Alright, so we have a 0 remainder. Okay, so therefore I can write the original polynomial in factored form. So we've got 2x cubed minus 3x squared minus 32x minus 15 is equal to x minus a -3, or x plus 3, times 2x squared minus 9x minus 5. Alright. Now it turns out we can factor this over the integers. Alright, so this is equal to x plus 3 times x minus 5 times 2x plus 1. So if you set the original polynomial equal to 0, then you'd be setting these equal to 0 equivalently, and then you could solve each of these separately. Alright, so the zeros are -3, which comes from this one, +5, which comes from that one, and -1/2, which comes from that one. So, possibilities for P over the possibilities for Q. So we've got plus or minus 1, that's it, for P. And then we got plus minus 1 plus minus 2 for q. So the possibilities for p over q. So start with a 1, plus minus 1 over plus minus 1 plus minus 1. Alright. Plus minus 1 over 2, you got plus minus 1/2. So you've got those four possibilities, and it turns out that 1/2 is what we're looking for. So there we go. All right. So therefore, the original polynomial 2x cubed minus 3x squared minus x plus 1 can be written in factored form as x minus 1/2 times 2x squared minus 2x minus 2. Now you can factor a common factor of 2 out of this second factor here, which I'll do. So you get x squared minus x minus 1. You can multiply this 2 times the first factor. So you get 2x minus 1, like this. Alright? Okay. Now, that factoring there makes this a little bit easier to work with. Alright? So, it's easy enough to solve that, set that equal to 0 and solve it for x. This one, though, cannot be factored over the integers. So, you could either complete the square or use a quadratic formula. Alright? We'll use a quadratic formula. X, or I will. X is negative b, so that's negative of negative 1 plus or minus the square root of b squared, or negative 1 squared, minus 4ac. That's 4 minus 4 times 1 times negative 1. All over 2a, or 2 times 1. So this gives you 1 plus or minus the square root of 1 plus 4, all over 2. And to continue up here where I have some more space. Alright, so that equals 1 plus or minus square root of 5 all over 2. And so what are the zeros? We've got 1/2 coming from this one here, or you could look at this one. Alright, what you do, or this one rather, set this equal to 0, solve for x. So you would set each factor equal to 0, solve for x. So you've got 1/2 as one of the zeros, and 1 over 2 plus or minus square root of 1/2 plus square root of 5 over 2. That's one of them. All I did was split up the numerator over the denominator. Alright, if you go backwards, start with this, you can get up to here. Alright, so they both have a common denominator, so you add the numerators, right? So you get 1 plus square root of 5 all over 2. And the same thing with the minus 1 over 2 minus square root of 5 over 2. So there are your 3 roots, 3 zeros.